Hello, good afternoon. My name is James. I work at Context Information Security over at Canary Wharf, and I'm here to talk about exploiting XML digital signature implementations. So specifically, I'm going to talk about some research I did into the implementations themselves, and I found quite a few interesting vulnerabilities while I was doing it. And so I'm going to go through some of these vulnerabilities. If you've ever seen a sort of presentation I've done before, you'll know there's going to be a lot of code slides probably later on, which show the vulnerabilities in action, and a few demos where I actually exploit the vulnerabilities themselves. Now, why would we care about this? So there's quite a few technologies which rely on XML digital signatures in order to verify the identity of a network resource or a network user. There's things like SOAP Web Security or SOAP Security, which is a security standard for adding sort of signatures or encryption to SOAP requests. There's also things like Visa 3D Secure, or Verified by Visa, as it's sometimes called, which apparently uses XML digital signatures to do verification of payments, but unless I sign a very large NDA and pay them a lot of money, they won't actually tell me what that is. So I can't actually give you any specifics on that, unfortunately. So I'm going to start with a little sort of story. Once upon a time, on a client site somewhere in Europe, if you can guess sort of where that is, then be quite good, quite impressed. This company was doing sort of an enterprise task management system. So they had a load of servers in their environment, and they wanted to configure them. So what they wanted to do was effectively have a single application running on those servers, which ran specific tasks, and you could then distribute those from the back end, send them to these servers, and it will do something for you. Now, they implemented this in .NET because their environment was primarily Windows, and because these task files were going to be XML, it seemed to make sense that they would try and sign them using some sort of private back-end key and make sure that these files can't be spoofed by attackers who are actually on the network. Now, they'd taken best practice. They'd looked on the internet, searched for how do you implement XML digital signatures securely, because there are some subtleties to implementing it which you need to make sure you cover. So they were fairly adamant they'd done everything they could to secure their environment. But of course, they made the mistake of trying to bait me into actually breaking their system. So I looked into .NET. I've done a lot of .NET work in the past, found a way of spoofing signatures in .NET, and therefore could run calc with local system on all their Windows servers, which is sort of quite a good day, really. Now, when I'm talking about implementations, these are the 5 I looked at. So what I'm actually talking about are the libraries which implement the XML digital signature specification. So there is Apache Santuario. Santuario is apparently a town in South America somewhere, not quite sure where. They have both a Java and a C++ implementation you can download, all open source. There's the XMLSec library, which marries up with libxml2, which is part of the GNOME project, and that provides the signature layer on top of that. There's .NET, obviously. I've already spoken about .NET. The Microsoft variant, and of course Mono as well. So Mono clones the .NET libraries for XML digital signatures. And finally, there's Java. So it turns out actually the implementation which comes with the JRE is actually the Santuario Java, but like an old version. So basically covering off 5 different implementations. Now, there are existing attacks, and these generally either come from bad uses of these libraries. So you're not verifying that the bit you signed was the bit you expected to sign, and this is sort of usually called signature wrapping, where you're able to move bits of XML content around and trick the verifier into verifying the wrong part of the document. But there's one which was more fundamental, and this was HMAC truncation. This actually has a specific CVE because it affected pretty much every single implementation of digital signatures at the time, and it even forced a change in the specification because it was pretty much just a limitation of specification. I'll go into a bit more detail of that later because I found a way of bypassing it in one of the libraries. And there's various others. So it runs XSLT, so if you know anything about XSLT hacking, there's potential fun in there. So I need to unfortunately describe sort of what I mean by XML digital signatures without describing the sort of structure of the signatures themselves. It's quite difficult to explain why some of the bugs work. And digital signatures is a W3 specification or recommendation, depending on what you want to call it. And this version is the latest version available, 2008, so it is about 5 years old. Although it goes back sort of a bit older than that. Now, if I wanted to sign a document, I may do something really, really naive. You know, I may take my XML document, I may read the bytes of that document, and then I may sign that document with some signature, and that generates a signature for that document. And okay, having two things is a bit of a pain, so I can stick them in some sort of container. So we've got things like SMIME, which does that for you, or PGP, which does that for you. And you've got your content and your signature, and they're two separate things. But to quote Steve Ballmer, or paraphrasing somewhat, that's not really how XML standards tend to work. If you're going to write something which implements digital signatures in XML, it better be parsed by XML, because those poor XML developers are going to have trouble parsing it otherwise. So this is the slightly more insane way of signing XML. So the first thing you do is you create a list of references. So it may be that you don't want to sign the entire document. You may actually just want to sign like a small subsection of it. That's fine. There's no problem with that. So we create a reference, and that reference refers to which part of the document, and we then run some transformation process on it. But ultimately, the end point is we get some bytes. We can then hash those bytes, say through SHA-1 or any other cryptographic digest algorithm. And we take that output from that process, and we generate a special signed info block. And this signed info block is a XML structure which contains information about what signature is being used, and also the list of references and the list of hashes for those references. We then perform another process called canonicalization, which converts that again to a series of bytes. And now we can finally actually do the signature. So we can sign it by our identity, whatever that may be, and then by the magic of XML, we can then shove that signature back into the same document, because why not? So what we end up is something like this sort of monstrosity. So we started with a document which has a good element. That was it. That was all it was in that document. And what we've ended up is this massive signature block. And it's sort of broken up into little bits. So we've got the signature element, which is wrapping the entire signature. We also have, at the bottom, the actual value itself. So this is the, say, the RSA SHA-1 padded signature value. We then have that signed info block. So this is the only thing which is actually signed. You don't directly sign XML content, you sign a list of hashes of XML content. And under there, you've then got your references. Now, when you come to verify this, it's sort of broken into three main areas. So if you pass in one of these files to a library and say, verify the signature on that thing, it has to first parse that signature. It has to take the XML content and work out what's the signature value, what references you're referring to, all that sort of stuff. It then has to verify that that signed info block is validly signed by some key, or so you can specify a specific key that it has to be signed by, and you can make sure that it's only a single person. And finally, you have to verify those lists of references. So you have to go through SHA-1 hash all the bits of the XML you want to look at and verify they are correct. Now, of course, from an attacker's point of view, those first two aspects are always going to be unauthenticated. Ultimately, you can't, so there's sort of a chicken and egg scenario with both of those parts of the pipeline. Turns out, interestingly, the reference verification isn't specified in the standard where you are supposed to do it. So in some implementations, it's actually done before the signed info verification, which means effectively that could be unauthenticated as well. So I've broken up the bugs themselves into those three main areas. So I will start with signature parsing bugs, go into reference verification bugs, and then signed info bugs. And the first one is something which I couldn't quite believe I could see in 2013, and it's a bug in Santuario C++, and it is perhaps one of the most trivial Stack Overflows you may ever see. And ironically, when they actually tried to fix it, they then introduced a heap overflow instead. Unfortunately, I didn't catch that one. Someone from ISEC Partners actually noticed that after they fixed it and got the CD out of it. Very disappointed. But it was a bug in the way in which they're parsing the identifier for which part of the document to actually extract. Now, the specification defines a few ways this URI attribute, as it is, can refer to what part of the document you want to assign. So right at the top, you have reference by ID. So an XML document can have an ID for a particular part of it, and you say, I want a reference by that ID, extract only that element. Now, more usefully, you can also say, just give me the entire document, because I just want to assign everything. And that's fine, and if you specify an empty string, it does that. Now, the next two are sort of holdout legacies from the old versions of the standard. Now, xpointer is sort of like xpath, and most people know what xpath is, but probably less people know what xpointer is. But effectively, all they've done is just define the same two primitives, reference by ID, and an entire document, in an xpointer syntax. And the interesting final one is actually, in certain processes, you can just slap in an arbitrary URL, and it'll go out and verify that file, which has some interesting consequences, which unfortunately I can't go into today because actually they haven't been patched yet. They were supposed to patch some of them this month, but unfortunately not. So this is the buggy coding question. And it is looking for one of these xpointer types, so it's specifically xpointer ID. And the goal of this function is to extract out that ID value and unparse it from the URI attribute. So they allocate a stack buffer, that's all great. Do a strlen on the URI to make sure, well, see how long it is, the input, and obviously know enough that you don't want to overflow a stack buffer, so we're going to verify that the length is not longer than the stack buffer, and then we proceed to completely ignore that for the rest of it. And as I say, it's one of the most trivial Stack Overflows you'll probably ever see. And there's even a second bug in that it never bothers to check whether there's a terminating character or not, which is great. And so to exploit that is actually remarkably simple. Create a signed XML document, change the URI reference to a long string of A's, and it's going to walk over your stack. And if you've got no stack cookies, fun can ensue. So I'm going to do a quick demo of this. So Shibboleth is an online identity provider. You can download some open source software which does sort of SAML verification. They're actually the people who write OpenSAML as well, so you probably come across that. And one of their products, Service Provider, which is used for verifying SAML requests, is written in C++ and uses the Apache C++ library. So this potentially is a service exposed to the internet running the vulnerable Apache library. So they're even generous enough to give you VMs to test out Service Provider. And so this is just pretty much standard VM from there. I think we did some configuration on it just to get it to work with identity providers, all that stuff. And one of my colleagues at work decided to put together a exploit for that vulnerability. So we've got in here sort of reverse shell, all ROP chains, all that sort of good stuff. So if I just start him up, and hopefully this will work, otherwise it's going to look very stupid. And it didn't work. Great. No, there we go. It's just taking a few seconds. And we have our shell, so we can obviously now run your usual stuff, ID. So fortunately, you don't get root. Not a remote root exploit, which is a bit of a shame. It's running as this shibd user, whatever, doesn't really matter. But obviously from there you can do obviously some interesting stuff, drop the password file, all that sort of stuff. So it's a fairly easy thing to exploit, because fortunately, for some reason, their libraries weren't even compiled with stack cookies, so there was no problem with actually exploiting that stack buffer overflow. So now I'll go on to reference verification bugs. I did have more parsing bugs, but due to time constraints, there's only so much time in the day, so continue with this. So this next bug is reliant on a certain property of certain thing they had to specify to make it more XML friendly, I suppose. And it comes down to the property of XML equivalence. So from a physical point of view, these two XML structures are completely different. But from a logical XML point of view, they're exactly the same, because if you ask it certain questions, so if you ask, what is the element name? Well, the element name is good. What is the value of the X attribute? Well, the X attribute is 1. And if you ask all these questions, they're effectively equivalent representations. So this does obviously cause a problem from a signature point of view. A signature, if you pass it through something like SHA-1, is obviously going to give you two completely different values. And that's a bit of a pain if you're trying to use that for verification of your files, because everything's contained in XML, and something in between you and the processor tweaks the XML slightly, that might break the signature and cause problems. So what W3C did was come up with canonicalization. And the idea here is if you have two equivalent XML documents, you can then apply a specific algorithm to it, called a canonicalization algorithm, which effectively takes those equivalent documents and always emits the same output representation. And then obviously, unsurprisingly, if you SHA-1 hash that, you only get one value. So now, of course, there would be an obvious bug in there if, for example, you could take two documents which were not equivalent, put them through that algorithm, and output the same output. Because then you could potentially take an existing signature signed document, modify it in some way, and output, and use that to be verified against the same signature. And this is what I found in Mono. So it turns out this bug is actually not fixed in Mono. I did try and reach out to Mono, and their stock explanation for security bugs seems to be more or less, fix it yourself. I can't fix it myself. I've spent too much time looking at the Microsoft.NET code, so basically it will be unfixed. It was also a bug in XML-sec1, or specifically in the canonicalizer, which is in libxml2. But it's interesting that it's actually the same author for both. And once I found the one in Mono, I actually recognized the author's name and then went and looked at his implementation in libxml2 and found the same bug. And again, W3C implemented this specification, or defined this specification, actually primarily so that XML digital signatures would work. It's sort of generating specifications for no other reason than to facilitate other specifications. And the bug in question was in the handling of attribute values. So when you've got an attribute in XML, you can actually represent it as single quoted or double quoted. Now, obviously, if it's in double quotes and you want to put in another double quote, you need to escape it in some form. And XML uses entity escaping like HTML. We put ampersand, name, semicolon. Now, in Mono, that worked fine. There was no problems with that. But there is actually a different type of attribute, and that's the XML namespace attributes. And in this case, they didn't do the output sanitization. So if you put a double quote into an XML namespace, you eventually get sort of XML injection attacks against the canonicalized output. Now, libxml2 turned out to be less vulnerable in this regard. You need valid URIs for your XML namespaces, but the developers got a bit lazy when they're doing their parsing, and for IPv6 style addresses where they're in square brackets, they decided that just anything within the square brackets is valid, at which point stick in a double quote and you've got your same attack. Now, to actually exploit that, you need a very, very specific set of circumstances, unfortunately. So I've come up with this naughty example. You have some sort of XML document which you're signing, and it has some sort of expiry element which says when that transaction expires. And this is in a separate namespace because namespaces are used, like you may go, someone's defined a timestamp or an expiry element somewhere else, therefore I may as well repurpose it, because then processors of expiries can work perfectly well. some stupid excuse for that, and it does happen. If you actually look at like XML encryption specification, it repurposes a lot of the digital signature specification for key information and stuff like that, rather than defining its own. So, and then we have a little bit of C# code for Mono, which just sees if it can find that expiry element and assumes if there's no expiry element in that namespace, that it's perfectly all right and it's not expired. But of course, with that vulnerability, if that content is signed, we can change the namespace to something which is completely different, arguably, because ultimately the namespace is based entirely on the string you've put in. So prior to that, when it parses it, it won't see the expiry element. But when the canonicalization process goes on for the referencing generation of the SHA-1 hash, it retransforms back to its original form, and you've now got your signature bypass. So, third bug. This again is Apache C++, and I don't want to make it sound like I'm trying to rag on Apache C++, but I am, because it's rubbish, or was rubbish until they fixed some bugs. And this is another signature bypass vulnerability. And it almost worked in Mono, except that Mono had a bug, which meant it didn't work. It crashed the processor. So it kind of is a DOS, but not really. I found quite a few bugs in Mono, which ultimately, through other bugs, they got away with, and they weren't exploitable because they blew up or crashed or just did stupid things. Now, if you go and look at how the C++ library verifies its content, when it's going through its reference verification, it goes into this piece of code, which then loads onto this piece of code, passing in a list of references. And finally, we get to this piece of code, which is just going to do a simple for loop across those references, checking each one in turn. But it's interesting to know if the list is empty, the for loop never gets entered, and what you effectively end up with is it returning true, because true is the default value. So if you can construct a signature with an empty reference list, and why you would have such a thing, I don't know, because you're effectively signing nothing other than the signature itself, fairly pointless, you could potentially get a signature bypass. So if you actually look at the code of how it actually constructs that list, it's, again, fairly simple. What it's doing is it's sort of iterating through the signed info block, going to each child. Once it's loaded up the other structures, it goes to look at hunting for references. And what it first does is it skips anything which it doesn't consider to be an element, because you can slap in a comment, for example, and you want to make sure you skip over the comments which are in the signed info block. If it then finds a valid element, it assumes it's probably a reference and therefore proceeds to load it. But obviously, if it doesn't do that, the list is empty and you could get a signature bypass. Now, how on earth would we actually affect that? So pretty much every implementation you see uses a DOM parser, an XML DOM parser, to construct a tree of the XML document and the signature. They didn't do a very good job specifying the standard, so that it's hard to stream an XML document and verify its signature at the same time. So when you parse the signature, it kind of looks like this from a tree structure point of view. We have, obviously, our signed info at the top, and under that, things like canonicalization information, signature information, and finally, our list of references. And so our load function does effectively that. It just linearly goes across that level of the hierarchy looking for reference elements. And obviously, if we have a comment, we can do something like this. The comment node will get ignored, but it'll still find the references at the end. So what we want is something which will do that, so effectively skip everything after we've loaded up the basics of the signed info block. So I looked at what child elements you could have, or what child nodes you could have in an element in a DOM tree. And this comes from sort of level 1 DOM core from way back when. And if we look at the element, we can have all the obvious stuff, so element, text, comments, all those sort of things. The last one is interesting, and it's called entity reference. It's like, what on earth is an entity reference? Well, you can see entity reference node there, and it seems to have the same list as as an element does. That's kind of interesting. And what an entity reference is it's related to document type definitions. And document type definitions allow you to specify arbitrary entities. So you can then use that and escape them in your code. And these could be external entities, but you can also have them local to the file. Now, most people use them for text replacement, but you can actually use them to replace parsed XML content. So in this case, we've got a B element, which we've stuck in the middle of an A and C element. And when we parse that using a DOM parser, we end up with a tree structure looking like that. And we have our A element and our C element, and stuck in between them is actually this entity reference node. And underneath that is actually our B element, which is the thing we want to try and hide. So you can kind of see where you might be able to exploit that. But, of course, it's going to apply some process to it. How is that even going to still verify? Because obviously we've kind of modified the structure of the XML document. That's not going to verify. But it turns out that in the canonicalization standard itself, there's an explicit example for what happens when you put in entity references. And what it does is it basically converts them into an inline structure. And obviously at that point, I sort of thought there was probably a bug in there somewhere for that. So yeah, if you apply the canonicalization to that original document, you parse that structure. So how would we actually exploit that in practice? Well, if we get a signed document, we can first take our reference element and package that up as an entity, shove that up into a document type definition at the top. If we then replace the entity, the element with the entity itself, what now happens is we end up with something like that. And so we get our bypass because effectively the parser ignores that completely. But crucially, when it goes to do the verification of the signature, it ends up back as its original form again, and it's all game over at that point. So that was reference verification. So now on to signed info verification. This is sort of the really crazy stuff if you're trying to actually exploit a signature parser. Exploiting the signature directly probably sounds like a good idea. So yeah, not ragging on Apache C++ at all, but it's them again, unfortunately. And this was a bug in their fix for 2009-0217, the HMAC truncation vulnerability. Now, it turned out, actually, through sheer ineptitude on their part, it ended up as a DOS instead of a signature bypass, which is a bit of a shame, but I could have maybe submitted the fix for the bug, then told them about the security issue and got a better idea out of it. I said it was a fairly big deal when this came out. People were like going, oh dear, whoops, we kind of screwed up on that one. And what it actually turns out to be is the standard, or the digital signature specification, allowed you to specify a HMAC output length attribute or element. And this defined the number of bits of the HMAC, if you're verifying using HMACs as opposed to, say, RSA, how much of that HMAC value you wanted to check. Now, apparently there is a security rationale behind this. It's basically along the lines of, if you have a truncated HMAC, it's harder to brute force the key and be sure that you've got the right key because you get aliasing against a shorter hash value. Complete bunk, in my opinion. But I'm sure probably someone better than me is to find that as a good idea. Now, the bug itself was no one told them to verify a lower bound for that length. So pretty much every implementation allows you to specify 0, at which point you checked no bits of the HMAC. Great, immediate signature bypass. Some were a bit more clever. They went out their way and at least ensured that you had to have a single valid bit in your HMAC, which is still ultimately brute forceable. So again, I looked at how they implemented this check in C++. And their code pulls out the output length. It's just a text node which contains an integer value. It then basically passes it to A2I, which is the C library function which converts an ASCII string to an integer. So presumably, that value is a signed integer. Okay, remember that? It goes through a few different steps until ultimately it gets to this function. And this function is where the actual fix is. You can even see the comment, fix 2009-0217, because obviously it's all good. So obviously the specification was changed, so it said the minimum length of the output should be at least 80 bits, or half the size of the hash value, whichever is greater. And this is what this check is doing. The output length is greater than 0 is actually due to, they use 0 to indicate that, that there is no output length specified. But if we look at output length itself, you'll notice it's now an unsigned int. And that's probably going to be a problem. So we then go into the next function, which is actually doing the verification. And I've already said that it's the number of bits, not the number of bytes. So the first thing you do is divide it by 8, because you want to get the number of bytes you want to check. And then, so we take the quotient from that. We use the C library div function to do this. We get the quotient, which is the number of bytes, and the remainder, which is the number of residual bits we want to verify. And then we compare it. So we just do simple two-step process, check the whole bytes for performance reasons, and then check the residual bits. But if we actually look at the div function itself, we actually notice that, well, actually it's taking signed integers again. So we end up with something which looks like that. And we end up with, if we specify HMAC output length of -1, that becomes all f's. And all f's then become 0 and -1, quotient of 0, so 0 whole bytes, -1 remaining bits, which ultimately ends up with max bits as all f's, and that obviously then can be used to be, because of the way the check works, that actually truncates everything to 8 bits. So 256 checks, or using sort of like statistical probability, probably only 128 brute force attempts, you can bypass the signature. Unfortunately, as I said, it was actually only a DOS. And that's because they clearly never actually verified, after they did the fix, which, because they set output length to 0, meaning use the entire hash, C++ implementation presumably was one of the implementations which would only verify 1 bit, because you couldn't have 0 bits. But obviously they never bothered to check that that worked, because when we're actually doing the residual bit check, we're iterating j, which is the number of bits, but incrementing I. And I is actually the index into the buffers we're referencing. So basically that's pretty much always going to, it's either always going to fail, unless by luck, or it's going to cause a crash if j, or if the thing never actually escapes. So it basically keeps going round and never hits the false loop. And that's basically what the DOS would be. So effectively the thing just blows up. So you can guess, it's kind of a difficult DOS to achieve because you still have to guess to the 8-bit values across your signature, but it's doable if you really wanted to DOS the platform. Now before I leave this piece of code, I thought I'd also point out something more interesting. And that is in the way they're doing the checks. Now, I don't know whether you might have seen a Black Hat talk in 2011 discussing remote timing attacks against HMAC processors. And ultimately, it came down to the fact that if you check the HMAC with a function which doesn't take a constant time, no matter what the input, you can exploit that timing difference to potentially brute force the HMAC. And this code is pretty much the canonical representation of a non-constant check against the HMAC. It's pretty much exactly the same as that paper actually specified when they were discussing it. So potentially, anybody using Apache C++ and doing HMAC verification is still vulnerable potentially to a timing attack against the HMAC verification. But I said I didn't want to rag too much on Apache C++, so I looked at a few others. So you look at Mono, for example. It looks almost like the same code. Of course, Microsoft is going to do it better. No, Microsoft didn't do it better. They did exactly the same code again. And even XML which, to be fair, was pretty much the best implementation I came across, even that had a problem in that it used memcomp, and memcompare is not guaranteed to be non-constant time. So, in fact, the only one which wasn't vulnerable was Java. And it turns out that about 2 or 3 years ago, someone pointed out that Java's function to verify HMAX in the library itself was a non-constant time check. And so Oracle, or Sun possibly as it was then, actually fixed that bug. And this is what the Java library relies on. And so actually, only by Java fixing that bug were they actually not vulnerable. Now finally, I can go back to my original story and talk about the .NET vulnerability. And this vulnerability actually has 3 CVEs, effectively. That's because I found it both in .NET, and then when I actually went to test it, it also surfaced in the Apache Santuario, and then by extension, the JRE. So all 3 of them need fixing. So strangely, they all get different CVEs. And I tried it on Mono, and Mono doesn't work because their implementation of XML digital signatures is not compliant to the Microsoft implementation. So they actually, by luck, got away with it. So if we go back to our signature again, so this is, again, a signed document of some kind. We see all these URIs, and it's like, well, what are all these damn things? They kind of look like namespaces of some kind. Specifically, this one, so canonicalization method, this is the description of what canonicalizer we want to use, because obviously one canonical algorithm wasn't enough. They wanted more than one, so there's like 4 different ones plus various others. And what these actually are is what they call algorithm identifiers. They're effectively unique URIs which indicate what algorithm to use. So they're used all over the place. So, for example, they have one for SHA-1. So if you want to specify what HMAC to use or what digest to use, you can specify the SHA-1 URI. Now, you could then replace that with the SHA-256 URI if you liked, if your implementation supports it. And we have various other ones like canonicalizers, XSLT transforms, all those good stuff. And if you look at the specification itself, it's kind of interesting in the way it words things. So it kind of talks about, well, we specified these, but they're not a complete list necessarily. So a implementation is free to add its own list of algorithms if it so desires. Now, extensibility mechanisms in crypto systems is usually a recipe for disaster somewhere along the line. And in this case, it was. So I looked at the way in which .NET was instantiating this canonicalization algorithm. So at its core, the .NET implementation has some function which will do the canonicalization process. And it must map from that string to some sort of instantiated object. Seems reasonable? Now, this is like a very stripped down version of the signed info class, which represents the signed info element. And we have a canonicalization method string, and this is that URI. We also have a canonicalization method object, which is the instantiated object to perform the canonicalization. And all we do, or all we did, was pass this name straight to this function, create from name. Okay? Maybe it's more specific than that. Well, we can go and look at the documentation for this function. And it sort of just says, create a new instance of something, cryptographic, something along there. In fact, even their example kind of goes, yeah, if you pass SHA-1 as that, you'll create a SHA-1 digest algorithm. That's kind of cool. So if you change the canonicalization algorithm to SHA-1, it'll create a SHA-1 digest object. It'll then blow up because it tries to cast it to a transform object, but it doesn't really matter. So I looked at what other things implemented transform. So stuck it in Reflector, obviously did its derived type generation, and I got a list like this. So we've got various things in here, like these are our canonicalization algorithms, they're in there. But we also start having things like base64 transform. Okay, it's kind of interesting, sounds pretty dodgy. Maybe the XPath transform. XPath transform takes an arbitrary XPath value and selects part of the document out for you. That's probably bad. And then I saw that the XSLT transform was in there, and I knew I was probably going to be onto something. So how would you actually exploit that in practice? If we took an existing signed document, we can then pull out the signed info block. This is the thing which is actually being signed. And we apply the original canonicalization mechanism to it and get a series of bytes. We can then convert that into a XSLT file, which only purpose is to re-emit those exact same bytes. And we can then modify our original signed document and then start changing anything we like, because effectively we bypass the signature mechanisms. So we end up with something which looks a bit like that. And that obviously doesn't look quite right. You've got an XSLT style sheet slammed in the middle of your signature, which is omitting the original signed info block. And notice there's not even any references anymore. .NET is another implementation which doesn't care if you have no references. So what it does, checks the signature, goes cool, and then goes, and there's no references to check. That's a signed file to me. So what it ends up doing, the processor extracts the style sheet and applies XSLT to it, which ends up with the same signed info block you started with. It then verifies that through canonicalization, verifies the signature, and you've got success. And awards are draped upon you. So I'm going to do a demo of that. So obviously I can't get hold of the particular software this company were using because it was their own internal developed software. So I've kind of knocked up my own little dodgy version of it. You have to bear with me. My computer crashed turning on the projector, so I need to restart my VMs. Hopefully it won't take quite that long. Come on. So what I'm going to show is basically I've got sort of a back-end system. This is the sort of server end, which contains the private key. And in theory, the private key will never be distributed outside of that server, and that's a secure server. And then you've got the client end, which has just the public key and has a program on it which will run, verify the signature of the task file, and then execute the process in which you specify. So I'll first generate a task. So we'll go for our well-known sort of like enterprise management program, Notepad. Just test that. Notepad pops up, cool. And we now specify our certificate, which I've obviously pre-generated. And we can call generate, and we can go, I'll just stick it on my web server, call it notepad.xml. Right. So if we now go back to our client end, we can go and download that task file. So this is what it looks like. So we've got our program, which is Notepad, in the XML document, and then some sort of signature block. And this is obviously signed by our back end, and our front end only has the public key available. So if I save that, okay. And I've associated XML with the actual program itself. So if I double click that, you get Notepad. Great. Now if I actually change that, so I want to go to my hacker tool of Calc. If I run that, it's going to tell me, no, sorry mate, that's not a valid task file. Signature's incorrect. I'm not going to let you do that. So some wily hackers wrote a bypass tool which will fix the signature for you. And we can run that against our XML file. So we run that. And now if we double click, we get a calculator. So, and if we look at the file itself, we obviously see our XSLT jammed straight in the middle of that, and calc's there. And obviously, subtly different from the other one. Okay. And that wasn't the only bugs I found. I found about 10 or so bugs as I was going across the implementations. There's a cross-platform denial of service. It pretty much worked on everything. In fact, the only thing it didn't really work on was XML-sec, and that's because they did some fixes in libxml2 recently to mitigate the DOS problem. You can steal files in certain implementations as well, which is kind of interesting. Some of their signature parsing was a bit weird. So the Java implementation, for example, doesn't care about the names of the elements. It just kind of just assumes that if they're in the right order, that's probably good enough for it. So you can end up with blended attacks. So if one processor processes it one time and another does it another time, you get it signed by two different people. And various other DOS stuff in .NET, and Mono getting lucky. Bastards. So that was my final score sheet. Obviously red means bloody hell. And clearly Apache C++ don't trust. But it's interesting that no one else had memory corruptions, which is not really surprising. And yeah, so pretty bad. And I think ultimately the takeaway sort of notes from this is basically don't trust your implementation. Things like the canonicalization trick can be fixed by verifying that the canonicalization algorithm is within a set of values you are willing to use. And the trouble was, because it's so loose and extendable, people are just going, if it says verify is true, that's probably all right for me. And I would probably stay away from maybe C++, or maybe better now, but definitely Mono, because they haven't actually fixed any of the bugs I told them about. Okay, so any questions on that?
Hi.
Yep.
How would someone go about checking the implementation in any given product for known bugs that have got CVEs? Is that a case of code review to see what library is being used?
Yeah, so historically, when I was looking for implementations or looking for things which actually use these libraries, like my primary mechanism was to just sort of do a review of the product and see what it was actually linking to effectively. So obviously from an open source point of view, you'll find that most of them use XML because it kind of comes with the GNOME platform. It's easier to handle, whereas Apache C++ is used in a very limited set of places. If it's running on Java, there's a very good chance it'll be using their own built-in implementation, and same with .NET. They'll most likely be using the built-in .NET versions.
Cool, thanks, James. On your scorecard slide, you mentioned file stealing.
Yep.
I may have missed it in the presentation, but what did you mean by that?
So that was just on the and the rest bugs. The DOS issue which I identified can also, for certain implementations, allow you to steal files using the well-known techniques, basically. Unfortunately, because they haven't actually fixed the DOS issue, I can't actually talk about that issue, which then talks about the file stealing issue. So, but you might be able to guess what it might be based on its XML. What can DOS XML? Okay. Well, thanks very much.
Thanks very much.
Thank you.